This is M2Q5. This particular question is not that difficult to solve because I went through the algebra in the lectures and I gave you the formula here as a hint, so you basically don't need to do anything. You just plug everything into the formula and then you'll get the answer. But in general, on the midterm, I can change the activation function and also I can change the cost function. So I do want to talk about, in general, what this question looks like so that you are clear what's happening. So the general problem is how to update using gradient descent. Here we're using something called the Sigmoid Perceptron update rule. It's basically another name for gradient descent for logistic regression. And in general, gradient descent is every time we update the weights by going in the negative direction of the gradient. And the gradient is with respect to the cost. And here we're usually only given one instance. So suppose the instance is I, then what we're doing here is essentially doing stochastic gradient descent. We're updating the weights according to just one of the instances, not the whole data set. So there are usually two main components, and this would be dCdA. So that's the cost function part, and then dA dW. And that's the activation part. So these are the derivatives that you need to compute. And here, if we combine them, we get a simple expression here. And also another implicit assumption with this sigmoid perceptron is that the cost function is cross-entropy. So we should write that down, and that is minus yi log ai minus 1 minus yi log 1 minus ai. So that's basically one possible loss with respect to that particular instance I. So usually we need the sum over all i's, but here I'm just going to compute a loss for one instance. What are the other possible ones? The one that's most often used is the square loss. So by the way, if I ask about these on the midterm, I will tell you, I will write down the loss function, because these, like square loss is not standard that we have a half in front, so I will tell you what it looks like in my version. So we will have the half in front. And what are other ones? So there's another one called the Hinge Loss, which is like the loss for SVM, but not exactly. And it's the max 0, 1 minus AIYI. And there are variations of this, so I need to specify which one I mean. So sometimes this is 2yi minus 1, because yi is 0, 1, or y could be minus 1 or plus 1. So it depends on how you label them. And the last one we talked about, I think, is 0, 1 loss. So it's basically counting how many mistakes we're making. So it's just counting whether AI is not yi, and that's not really differentiable. If you differentiate this thing, I think it's just 0 everywhere except for like at one point when they're equal. So that's not differentiable, so we don't use gradient descent with this. Okay, so that's the cost function part. And the other hard part is the activation function. So we have our logistic activation. So let's copy that. Let's say this is the activation. So the first one is logistic. It's 1 plus e to the minus z. And whenever I write z, z is always w transpose x plus b. So I'll not repeat that. And that would be our AI. And then the derivative of AI with respect to one of these w's is just AI 1 minus AI. So that you can either, every time you just differentiate this function and then you realize it is that, or you can just remember it. Because logistic activation are often used, so you can remember it this way. And also remember, you always need to multiply by x because of the z part. When we differentiate z with respect to this W, you get an X, and this X is Xj corresponding to Wj. So I will not write it here, and I will just write the Z here for simplicity. And what's the other one that we have as activation? I know there's the LTU, but LTU is not differentiable, so we don't use it often. So LTU is basically whether Z is larger than or equal to 0. That's our AI. And there's, again, differentiating this doesn't make sense. It's 0 everywhere. So we're not going to do that. And what's the other one? Hyperbolic tangent. We talk about hyperbolic tangent actually in the recurrent neural network lecture. So it's, as the name suggests, it's just hyperbolic tangent of Z is our A. And it turns out the derivative is 1 minus AI squared. And you can remember this, or you can try to actually differentiate this. You can write this in the exponential form and differentiate that. And what are the activation function do we have? ReLU? Yeah, the fastest one. ReLU, and it's just Z multiplied by Z larger than or equal to 0. And that derivative with respect to Z is either 1 or 0. And if Z is larger than Zi is larger than or equal to 0, then it's 1, and otherwise it's 0. So these are basically the derivatives. So now we get the list of the things that we know, and there may be some others, simpler, algebraically simpler activation functions or cost function that I might put on the midterm, but the derivatives will be easier than doing these. In any case, so we have this part, and derivative these things should be very easy to differentiate. So let's actually do the one that we have here, the cross entropy combined with our logistic. So the goal is finding minus alpha dCi, dAi, and dAi dW. So first, the cross entropy derivative is, I spent a long time during the lecture to talk about this, so I'll write that down quickly. Hopefully I get it right. So AI minus Yi divided by AI1 minus Yi. So just go back here and differentiate this expression and then combine the two fractions and then simplify it, then you'll get expression like this. And then you have here this logistic derivative, so that's AI1 minus AI. So the good news is that they cancel out. And remember, this is with respect to Z, and Z with respect to W is just X, is always X. And to be very formal, we should have J here and J here, so that it's actually partial derivative, not a gradient vector. But it turns out we can just combine them into a vector, so I'll just leave it like this. And then you are just multiplying alpha in front, and that's our change in W in one step. So that's why if we go back, we have an expression like this.